If we could look at the universe without stars, without nebulae, without the glowing spirals of galaxies, we would discover a structure far grander than anything the eye can normally see. Every galaxy we know, from tiny dwarfs to giant ellipticals, is not floating randomly in space. Instead, each one is strung like a bead on vast, invisible threads of matter that span hundreds of millions of light years. This hidden architecture is known as the cosmic web, and it is the true shape of our universe. At first glance, the cosmos seems chaotic, billions of galaxies scattered across a dark and expanding void. But when astronomers began to map their positions in 3D, a completely different picture emerged. Galaxies gather into long filaments, weaving together like tendrils of smoke. These filaments form nodes, and those nodes grow into clusters, immense cities of galaxies bound by gravity. Between these structures lie enormous cosmic voids, empty regions so vast that a beam of light can cross them for hundreds of millions of years without encountering a single star. This web-like structure did not arise by chance. Long before the first star ignited, before any galaxy existed, the universe already carried faint ripples in its density, tiny seeds imprinted during the earliest fractions of a second after the Big Bang. Over billions of years, gravity amplified these ripples, drawing matter into a cosmic skeleton woven mostly from dark matter, the invisible substance that outweighs ordinary matter 5-to-1. It is this dark framework that dictates where galaxies form, how clusters grow, and how the universe looks today. Before the first stars lit the darkness, the universe had already built its bones, a silent scaffold made of shadows and gravity. In this video, we will explore the structure that shapes everything, the filaments that stretch like intergalactic rivers, the vast empty voids that carve open cosmic deserts, the clusters where thousands of galaxies collide and merge, and the enormous superclusters that form the largest coherent structures ever observed. This is the story of the cosmic web, the hidden skeleton of the universe. The idea that the universe might have a hidden structure is surprisingly recent. For most of the 20th century, astronomers assumed that galaxies were scattered more or less randomly throughout space. A few clusters here, a few groups there, but nothing resembling an organized pattern. The cosmos seemed messy, unpredictable, noisy. Then, in the early 1980s, something remarkable happened. Astronomers began creating the first redshift surveys, three-dimensional maps showing not only where galaxies appeared on the sky, but also how far away they were. When the first slices were plotted, researchers expected a cloud of points. Instead, they saw shapes. Across the maps, galaxies were not evenly sprinkled. They gathered into arches, walls, and long comb-like ridges. One of the most famous early discoveries was the so-called Great Stickman or Comb, a massive, tooth-like structure where thousands of galaxies lined up along an enormous filament. These earliest maps revealed something shocking. The universe was not chaotic. It was patterned. By the 1990s and 2000s, technology transformed these early glimpses into full cosmic cartography. The Sloan Digital Sky Survey, SDSS, mapped millions of galaxies across huge volumes of space, revealing vast filaments stretching hundreds of millions of light years. The Dark Energy Survey, DES, refined our view even further, tracing how dark matter shapes the cosmic web through gravitational lensing. Today, cutting-edge missions like DESI and Euclid are charting the positions of tens of millions of galaxies with unprecedented precision, turning the cosmic web from a theory into a directly observed phenomenon. These new surveys uncovered features far larger than anyone imagined. Gigantic walls of galaxies spanning billions of light years. Enormous voids, so empty they contain almost nothing at all. And superclusters, where galaxy clusters merge into colossal chains. With every new map, one truth becomes clearer. The universe is not a random sea of stars. It is a woven structure, with patterns imprinted from the earliest moments after the Big Bang. Long before the first star ignited, before galaxies had names or shapes, the universe was ruled by something we still cannot see. Dark matter, an invisible substance that makes up nearly 85% of all matter in existence, became the silent architect of everything that would follow. If ordinary matter is the paint of the cosmos, dark matter is the canvas beneath it. In the first few 100,000 years after the Big Bang, the universe was a hot, smooth fog of particles and radiation. Light bounced around endlessly, nothing yet resembled a structure. But dark matter behaved differently. It did not interact with light. It felt only gravity. And so, while photons pushed ordinary matter around, dark matter quietly clumped together, forming the earliest gravitational wells, primordial pits in the fabric of space-time. These wells, or potential wells, acted like cosmic basins. As soon as the universe cooled enough for atoms to form, ordinary gas began to flow into these invisible depressions, collecting wherever dark matter had already gathered. The cosmic web, the entire structure of filaments, nodes, and clusters, owes its existence to this invisible scaffolding. Simulations show that dark matter filaments formed first, long before the birth of light. These strands provided the gravitational framework that dictated where galaxies would eventually appear. Without dark matter, gas in the early universe would have remained too smooth, too evenly spread, to collapse into stars. There would be no galaxies, no clusters, no cosmic tapestry at all. This is why the cosmic web formed before the cosmic dawn. Even in perfect darkness, long before light traced the universe's skeleton, dark matter had already drawn the outlines of everything to come. The first stars merely illuminated what was already written. Today, we still do not know what dark matter is, whether it is a particle, a field, or something entirely unexpected. Yet we can see its fingerprints everywhere, in the rotation of galaxies, in gravitational lensing, in the shape of the cosmic web itself. It remains the greatest architect we have never seen. The cosmic web did not begin with galaxies, or gas, or even dark matter itself. Its story began in a time so early, so impossibly brief, that human language struggles to describe it, the inflationary era, when the newborn universe expanded faster than the speed of light. During this instant, lasting far less than a trillionth of a second, the universe was governed by quantum rules. Space itself was a storm of microscopic quantum fluctuations, tiny, random variations in energy, smaller than the size of a proton. These ripples were not meant to last. Under normal circumstances, they would flicker into existence and vanish again. But inflation changed everything. As the universe ballooned outward, these quantum fluctuations were stretched across cosmic scales. What began as subatomic imperfections became vast regions of slightly different density, some a little heavier, some a little lighter. These subtle differences, 1 part in 100,000, became the primordial seeds of all cosmic structure. Where the density was slightly higher, gravity would one day pull matter inward, forming the nodes of the cosmic web. Where it was slightly lower, matter would drift away, leaving behind the future cosmic voids, enormous dark caverns spanning hundreds of millions of light years. It is one of the most astonishing truths of cosmology. The entire skeleton of the universe originates from quantum noise. The filaments, clusters, voids, and superclusters we observe today are enormous echoes of these early fluctuations. Inflation froze them into place like ripples on water suddenly turned to glass. And over billions of years, dark matter and gas responded to this primordial blueprint, amplifying tiny differences into the grand structure we see across the sky. The cosmic web is not just a pattern, it is the magnified imprint of the smallest possible fluctuations in the earliest moment of time. The universe today is a scaled-up portrait of its own quantum beginnings. If we could step outside our galaxy and observe the universe on the largest scales, we would see something astonishing. The cosmos is threaded with enormous glowing rivers of matter. These are the filaments of the cosmic web, colossal strands made of dark matter, hydrogen gas, and billions of galaxies strung along them like beads on an invisible wire. Each filament can stretch hundreds of millions of light years, making them some of the largest structures ever discovered. Yet they are not random. They formed exactly where the early density variations from inflation were strongest. Gravity amplified these regions, pulling dark matter into long, interconnected highways. Ordinary matter, gas, dust, plasma, followed the invisible pull of dark matter, settling along these vast structures. Galaxies are not scattered throughout the universe like stars in the sky. They grow along filaments, feeding on the steady flow of gas that streams inward like a cosmic river. It is along these threads that the universe builds its grandest architecture. Star formation, galaxy evolution, even the growth of supermassive black holes, all are influenced by their position within the web. Filaments serve as the universe's transportation network. Cold gas, the raw material for new stars, flows down these enormous gravitational channels and pours into galaxy clusters at the nodes of the web. These inflows can reach millions of degrees, creating shock fronts and igniting the intense activity often seen in cluster cores. Without filaments delivering this cosmic fuel, clusters would starve, and galaxies within them would fade. We have observed several of these megastructures directly. The Sloan Great Wall, a vast chain of galaxies over 1 billion light-years long. The Hercules A Corona Borealis Great Wall, one of the largest known structures in the observable universe. The cosmos web observed by JWST, capturing delicate filaments feeding young galaxies in the early cosmos. The cold streams of the early universe, where gas funneled into forming galaxies along narrow filaments, igniting starbursts. These structures reveal a breathtaking truth. Galaxies are not isolated islands. They are the product of these immense cosmic rivers. The filaments define where galaxies grow, how they cluster, and even how the universe evolves on its grandest scales. They are the arteries of the cosmos, carrying matter where it is needed most, shaping everything we can see and everything we cannot. When we picture the universe, we often imagine clusters of galaxies, bright filaments, and swirling nebulae. But most of the cosmos is something very different. Emptiness. Not absolute emptiness, but vast cosmic voids, enormous regions where galaxies are scarce and matter is stretched thin across unimaginable distances. These voids are not small, accidental gaps. Some span hundreds of millions of light-years in diameter, making them among the largest structures in the observable universe. If a typical galaxy were the size of a grain of sand, a cosmic void would be a hollow sphere the size of a city. Their density is so low that entire superclusters could pass through them without disturbance. And yet, these voids are not merely empty bubbles, they are essential to the evolution of the cosmos itself. Voids formed from regions where initial inflationary fluctuations were slightly underdense. As gravity amplified the overdense regions, forming filaments and clusters, these underdense regions grew emptier and pushed outward. Over billions of years, matter flowed away from voids and into surrounding walls, leaving behind enormous stretches of space that appear silent and deserted. But voids are dynamic players in the cosmic drama. Because they contain so little matter, there is almost no gravity pulling inward. This means that voids expand faster than the average universe, subtly pushing on the denser regions around them. They help shape the boundaries of filaments and superclusters, acting as the negative imprint of the cosmic web. Voids also leave fingerprints on the oldest light in the universe, the cosmic microwave background, CMB. A photon traveling through a large void loses slightly more energy than it gains on the way out, due to the changing gravitational potential of the expanding void. This phenomenon, known as the Rees-Asayama effect, creates tiny temperature imprints on the CMB map. These imprints are so faint that only with the most sensitive measurements, from missions like Planck, can we hope to detect them. So even the universe's emptiest places are far from irrelevant. Voids influence how galaxies grow, how the cosmos expands, and how its oldest light shifts as it travels. They are the quiet counterbalance to the dense knots and threads of the cosmic web, the dark, yawning deserts that give the universe its structure and rhythm. If the filaments of the cosmic web are rivers, then the universe also contains something even grander. Cosmic walls, vast continents of galaxies stretching across unimaginable distances. These are the regions where multiple filaments converge and interlock, forming immense sheets of matter that define the boundaries of cosmic voids. One of the first and most famous examples is the Sloan Great Wall, discovered in 2003. It spans nearly 1.4 billion light-years, making it one of the largest known structures in the observable universe. When astronomers first mapped it, they realized that what looked like scattered galaxies were actually pieces of a single, enormous formation stitched together by gravity. Then came the South Pole Wall, revealed in 2020. Hidden behind the Milky Way's galactic plane, it curves like a colossal arc, enclosing one of the biggest known cosmic voids. Measuring roughly 1.4 billion light-years long, it demonstrates just how sculpted and interconnected the cosmic web truly is. But perhaps the most astonishing structure is the Hercules Our Corona Borealis Great Wall, a titanic chain of galaxies stretching more than 10 billion light-years. If it is truly a single structure, and some astronomers doubt this, it is so massive that it appears to violate the cosmological principle, the foundational idea that the universe should look roughly the same in all directions and on all sufficiently large scales. A structure this large challenges our assumptions about uniformity and randomness in cosmic evolution. Regardless of the debate, these walls illustrate a profound truth. They are the result of filaments merging and locking together, forming the backbone of the largest patterns in the universe. They act as continental plates of galaxies, defining the edges of voids, regulating matter flow, and anchoring galaxy clusters. To visualize them is to grasp the scale of the cosmic web, a universe where galaxies are not floating in chaos, but arranged along grand architectures that span billions of light-years. These walls aren't solid, of course. They are thin, porous sheets of stars, gas, and dark matter. Yet on cosmic scales, They are as monumental as mountain ranges. They show that the universe is not only vast, it is structured, layered, and astonishingly organized. At the intersections of the cosmic web, where multiple filaments converge like highways meeting at a grand interchange, lie the most massive gravitational structures the universe can form, galaxy clusters. These are not just groups of galaxies. They are vast, multi-component worlds, binding together everything from dark matter to scorching plasma to thousands of swirling star cities. A typical galaxy cluster contains hundreds or even thousands of galaxies, all orbiting a common center of gravity. Yet the galaxies themselves are only the visible fraction of the whole. The true mass of a cluster is hidden in two places. The first is dark matter, which makes up roughly 80% to 90% of the cluster's mass. This invisible scaffold provides the deep gravitational well that holds everything together. Without dark matter, clusters simply could not exist. Their galaxies would drift apart over cosmic timescales instead of remaining bound. The second major component is something we can see: hot intracluster gas, heated to tens of millions of degrees. This plasma glows in X-rays and fills the space between galaxies. In fact, the gas in a cluster often outweighs the galaxies themselves. It is so hot and diffuse that it forms a shimmering atmosphere larger than entire galactic groups, making clusters not just gravitational structures, but thermodynamic ecosystems. Clusters form precisely where they do, at filament intersections, because matter naturally flows along the threads of the cosmic web. Like rivers feeding into a basin, gas and galaxies fall toward these nodes, gradually building up enormous structures over billions of years. The densest knots in the cosmic web become the brightest and most massive clusters. Two famous examples show just how complex and powerful galaxy clusters can be. The Coma cluster, a chaotic, massive cluster containing over 1,000 galaxies. It is one of the strongest pieces of evidence for dark matter. Galaxies move so fast within Coma that, without dark matter binding the cluster, the entire structure would fly apart. The Virgo cluster, our local giant, sitting less than 60 million light-years away. The Milky Way is part of the Virgo supercluster, slowly falling toward Virgo's gravitational center. Virgo is a living demonstration of how galaxy clusters shape the fates of cosmic neighborhoods. The gravity of these clusters is so immense that it bends light itself, a phenomenon known as gravitational lensing. Distant galaxies behind a cluster appear stretched, distorted, or even multiplied, their images warped by the curvature of space-time. This lensing is not just a stunning visual effect. It is a direct measurement of the cluster's mass, allowing astronomers to map the invisible dark matter halo that envelopes the cluster. Galaxy clusters are the beating hearts of the cosmic web, nodes where gravity, matter, and time converge. They remind us that the universe's largest structures are not chaotic but deeply interconnected, shaped by the invisible architecture of dark matter and the relentless pull of gravity. Beyond galaxy clusters lies an even grander scale. Superclusters, the megacities of the universe, where dozens of galaxy clusters are loosely connected in sprawling, continent-sized structures. While clusters are the gravitational hearts of the cosmic web, superclusters are its vast metropolitan regions, stretching across hundreds of millions of light-years. A supercluster is not a single-bound object but a flow pattern, a region where gravity channels matter along large-scale currents. It is a roadmap of how galaxies move through the expanding cosmos, guided by the hidden pull of dark matter and the push of dark energy. Our own home resides inside one of these extraordinary structures, the Laniakea supercluster, Hawaiian for immense heaven. Laniakea spans more than 500 million light-years and contains over 100,000 galaxies, including the Virgo cluster, the Hydra-Centaurus region, and our entire local group. When astronomers mapped the motions of galaxies within this region, they discovered that everything flows toward a common gravitational center called the Great Attractor, a mysterious concentration of mass-pulling galaxies across enormous distances. Laniakea is defined not by boundaries on a map, but by the direction of cosmic rivers of motion. If galaxies stream the same way, they belong to the same supercluster. These flows reveal a deeper truth. Superclusters are not gravitationally bound structures. Because of dark energy, the universe's expansion accelerates, stretching space faster than gravity can pull it together. This means that superclusters are temporary alignments in the cosmic web, patterns that exist today but will eventually drift apart on cosmological timescales. Yet, even if they are not eternal, their scale is awe-inspiring. They are the largest coherent structures we can define, each a vast, shimmering district of the cosmic web. They show us how matter organizes itself across unimaginable distances, and how the interplay of gravity and dark energy sculpts the visible universe. Standing inside Laniakea, we are tiny residents of an immense cosmic city. One connected neighborhood in a universe woven from threads, clusters, and rivers of stars. The cosmic web is not a static structure. It is alive, stretching, thinning, tightening, and drifting as the universe ages. Over billions of years, gravity and dark energy reshape the vast architecture of filaments, clusters, and voids, slowly transforming the visible cosmos into something very different from the universe we see today. In the early epochs, filaments were faint threads, wisps of dark matter pulling gas into long, fragile structures. But as time passed, filaments grew denser, accumulating mass from every direction. Gas funneled into them like rivers feeding a basin, igniting new generations of galaxies. Each filament became a cosmic highway carrying matter toward the nodes, the galaxy clusters, strengthening the skeleton of the universe. Meanwhile, voids expanded. Where filaments gathered matter inward, the voids pushed outward. These underdense regions, free of significant gravitational pull, stretched faster than the cosmic average. As galaxies drifted away, the voids became vaster, hollower, and darker. Today they take up most of the volume of the universe, and their reach continues to grow. But the most profound force shaping the future of the cosmic web is dark energy. This mysterious pressure accelerates the expansion of space itself. As the universe expands faster and faster, the ability of gravity to form new large-scale structures weakens. Filaments no longer pull in matter as efficiently. Small structures stop merging. The cosmic web begins to freeze, its growth slowing to a cosmic crawl. And in the far future, trillions of years from now, the transformation will be complete. The filaments will become incredibly thin, stretched by the accelerating expansion. Their once dense streams of galaxies will separate into isolated islands, each drifting away into the darkness. The clusters will remain bound, but the bridges between them will fade. The cosmic web will look like a sparse collection of distant lights suspended in a vast, empty sea. The voids, meanwhile, will balloon to unimaginable scales. They will dominate the universe, swallowing the spaces between the last gravitationally bound structures. The cosmic web will fade into a delicate, ghostly remnant of its former self, a memory written in gravity. And eventually, future observers, if any still exist, may not even see the web at all. They'll live inside isolated structures, unaware that the universe was once rich with filaments stretching across hundreds of millions of light years. The cosmic web, magnificent and intricate today, is only a temporary tapestry, a fleeting architecture sculpted by gravity, stretched thin by dark energy, and destined to dissolve into the quiet darkness of the far future. When we step back far enough, far beyond clusters, filaments, and voids, a profound assumption emerges: the cosmological principle. It states that on the largest scales, the universe is homogeneous and isotropic, roughly the same everywhere, no matter which direction we look. This principle underlies nearly every equation in modern cosmology. But is it actually true? Our maps of the cosmic web show repeating patterns of filaments and voids extending for hundreds of millions of light years. In every direction we observe, the structure looks similar: knots, threads, walls, and empty regions, woven into the same colossal tapestry. This symmetry suggests that the cosmic web may indeed continue indefinitely, a repeating pattern stretched across the universe. Yet we face a profound limitation. We can only see the observable universe, a spherical region about 46 billion light-years in radius. Beyond this boundary, light has not had enough time to reach us since the Big Bang. Everything outside remains hidden, not because it isn't there, but because physics prevents us from seeing it. So our cosmic web, the structure we admire, might be only a tiny fragment of a vastly larger, potentially infinite network. But could the pattern repeat forever? Some theories say yes. The cosmic web may be an infinite fractal, with structure at all scales, repeating patterns that go on without limit. Others propose that the universe may have a non-trivial topology, a shape that wraps around itself, like the surface of a sphere or a higher dimensional torus. In such a universe, traveling far enough in one direction could theoretically bring you back to your starting point, and the cosmic web might be finite yet unbounded. The truth is that we don't know. We see the web only within our cosmic horizon, and all signs point to a structure that looks the same in every direction. But whether this repeating pattern extends forever, or whether the universe folds into a grand, self-contained geometry, these remain open questions at the edge of cosmology. What we can say is this: the cosmic web is not merely a local phenomenon. It is the universe's signature, the natural outcome of gravity sculpting matter across time and space. Whether it repeats infinitely or curves back on itself, it represents the deep, inherent structure of the cosmos. And beyond our horizon, unseen and unreachable, the same invisible threads may continue, weaving the skeleton of a universe far larger than we can ever observe. Understanding the cosmic web is not just an abstract scientific pursuit. It is the key to understanding why the universe looks the way it does, and why we are here at all. The cosmic web is the blueprint of structure formation. Every galaxy, every star, every planet traces its origins back to the invisible scaffolding of dark matter that formed in the earliest moments after the Big Bang. Without these threads, matter would never have gathered into clusters, never cooled into disks, never collapsed into the luminous stars we see today. By studying the web, we learn how galaxies are born, how they grow, and why they evolve differently depending on where they live. Galaxies in dense filaments form stars more quickly, merge more often, and grow larger. Galaxies in voids live quieter, more isolated lives. Even the destiny of a star system, whether it becomes part of a cluster or drifts in solitude, is determined by its place in this grand network. The cosmic web shows us that the universe is not random. It has structure, hierarchy, and order, a vast architecture shaped by gravity and the unseen influence of dark matter. The sun itself formed inside a filament, in a galaxy drawn along cosmic flows established billions of years before Earth existed. And this is the ultimate relevance. Without the cosmic web, none of this would exist. No galaxies, no stars, no solar systems, no chemistry, no Earth, no life. We are not separate from the web. We are one of its outcomes, a quiet spark formed on a tiny planet, inside a small star, inside a galaxy guided by dark threads stretching across the universe. To understand the cosmic web is to understand the deep ancestral structure that shaped the entire cosmic story, including our own. In the boundless darkness of space, there exists a hidden framework, an invisible lattice that holds the grand shape of everything we know. It is a structure we never see directly, yet it threads through every corner of the cosmos, guiding the birth of galaxies, stirring the first murmur of stars, and shaping the quiet destinies of worlds. We live upon one delicate strand of this immense web, unaware of how profoundly it has sculpted our existence, how every atom in our bodies once followed the currents of these ancient cosmic rivers. The cosmic web is more than a structure. It is the skeleton of reality, the silent geometry upon which the universe has written its unfolding story. Long before Earth existed, long before the first star lit the darkness, these filaments stretched across space, forming pathways that matter would follow for billions of years. And now, as we explore its vast and intricate design, we glimpse something deeper, a reminder that even in the largest scales imaginable, there is order, connection, and lineage. The web is not simply out there in the void. It is the ancient architecture we arose from, the quiet blueprint that made the universe capable of creating itself, and eventually, capable of creating us.